Carrying on with the next handout that was done in class, so differentiation practice. All right, preamble. You're comfortable at this stage with finding the first, second and third derivative. I know I didn't discuss those, so I will, of a polynomial function like this, right? So we're comfortable with how to do differentiation on that. So question 1, find all the derivatives of the function above. So here's f of x. I'm going to write it out, so should you. 3x to the 4 minus 1.7x cubed plus 8x squared plus 2.6x minus 21. All right. Now if we differentiate, then we get f dash x. So 3 4s are 12, so we've got 12x cubed. Now 1.7 times 3 is 5.1, so 5.1x squared, and then 16x, and then plus 2.6. So that is the first derivative. Right, what's the second derivative? Well, we differentiate again. Derivative. Right, we differentiate again. So, and this is f double dash x. So 12 threes, that's 36x squared. And then 5.1 times 2, that's 10.2x. And then that's plus 16, and then nothing. Right, now the third derivative, f triple dash x. So 36 times 2, that's 72x minus 10.2. And then the fourth derivative is just 72. And the fifth derivative, now putting so many dashes gets annoying, so that's 0. Right? So this notation tells you the fifth derivative, right? And normally I'd do that as well for there, but first, second and third derivative can just have dashes. Okay, and then we're not going to take any more derivatives, they'll just all be 0. All right, so that's the first, second, third, fourth and fifth derivative. I just want to make a quick comment about it. What is a derivative, right? If you've got a function, then we talk about the gradient at a point, right? Or the gradient of that tangent. What that really means is, if you are only looking at one small part of the function and you said, oh, I want to approximate this with a line, then that this is not a great approximation, but it's the best approximation you'll get to line. And we use the first derivative to find that. If you say, okay, I want to approximate this with a parabola, you'll get a better approximation. It won't be perfect because this shape is not a parabola, it's a quartic. It can't be made to look exactly like a parabola, but you could get, just in this region, you could get like a parabola that happens to look something like that. That's a good approximation in that area. Now, this is beyond the scope of high school, but to create that parabola, you would look at the first and the second derivative, right? If you wanted to make it a cubic, say some kind of cubic that is a good approximation in that area but completely fails over here, then you'd be looking at the first 3 derivatives, right? To make a quartic, you'd be looking at the first 4, but then you'd get this perfectly because that is it is a quartic, okay? So that's just a little commentary about the significance of first, second, third, fourth, and so on derivatives. Quick as you can, write the 30th and 31st derivatives of x to the power of 30. Now, I'm going to explain this over the course of about a minute. I'd encourage you to pause and try it yourself first, but it might take you more than a minute. Right, here we go. Let's say I go y dash equals x to the 30, or f of x equals x to the 30. I'll just stick with this notation for now. Right, so what's f dash x? Well, that's 30 times x to the 29. And what's the second derivative? Rather than me actually calculate 30 times 29, I'm just going to go, that's 30 times 29 times x to the 28. Right, one more. F triple dash, the third derivative, 30 times 29 times 28 times x to the 27. You can see what's going on here. This is going to have something to do with 30 factorial, isn't it? Going to multiply all the way down to 1. Well, let's have a look up here. A degree 4 polynomial had its fourth derivative was a constant, and the fifth derivative was 0. Okay, so for a 30th degree polynomial here, right, the 30th derivative is going to be a constant, and the 31st derivative is going to be 0, right? And this is going to be 30 factorial. Okay, are you going to be asked that in an exam? No, but it's interesting. Okay, we now look at questions that require algebraic manipulation. So we're going to expand or divide through these in order to get the derivative. So A, f of x can be rewritten as x to the 4 minus 10x cubed, and so f dash x is 4x cubed minus 30x squared. There we go. So we had to expand first. You can't, at the moment, we don't know how to differentiate something that looks like that. And we don't need to because we can just expand it. B, once again, we're going to expand. So so this expands to 2x squared plus x minus 6. So f dash x is 4x plus 1. And C, this time we're dividing through. So I'm going to take out the 1/7, right? This 7 here can just come out the front as a 1/7. That's just good technique. And now divide through by x. So I get x to the 4 minus 4x cubed plus 2x squared. So that's f dash x. And f of x is now the 1/7, nothing happens there. And I get 4x cubed minus 12x squared plus 4x. Okay, done. Now just a note about notation. I don't ever want to see you do something like this. You know, you've got f dash x equals 2x squared plus x minus 6, and you've been told to differentiate it, or you need to differentiate it for some reason, and then you do this. That's 4x plus 1, right? That is absolute rubbish. That does not equal that, okay? They're different things. It's essential that you label what you're doing, right? It's a different thing. But that's something that a lot of students do all the time. And I guarantee you those are not the students that are getting the best marks. All right. A key purpose of differentiating is to substitute particular values into f dash x to find the gradient of the tangent, right? So we're going to do that here. So question 4, consider f of x equals that. So part A, we're going to sketch this parabola. And I'm going to sketch this pretty much as well as I can. So like in more accurate detail than I would normally do a sketch. So I think those are, perpendicular. The x-intercepts are -1 and +3. Right, so I've got to go through there and there. The axis of symmetry is x equals 1. And if I mentally substitute x equals 1, then I get y equals -4. So I'm going to try to make the same scale, 1, 2, 3, 4. And so I end up here at 1, -4. And I'm going to try to sketch out this parabola nicely. Okay, so I've done a pretty good job there, and it's going to have a y-intercept of -3. Right. So part B, so that was A. Part B, find the derivative after expanding. So f of x is x squared minus 2x minus 3. So f dash x is 2x minus 2. Right, so that's done. Part 3, find the gradient of the tangents at the points where the curve intersects the x-axis. So I'm just going to draw in those tangents. something like that, and something like that, right? It's not going to be perfect, but that's fine. I want what we're doing here to have meaning. Right, so I'm going to find the gradients. Well, what I do is I'm going to sub x equals -1 and x equals 3 into f dash x, because that finds the gradient of a tangent. Right? Okay, so that's the thinking. Here's actual working. Right? I'd like you to copy this in exact detail. The point -1, 0. We have f dash -1 equals 2 lots of -1 minus 2. That's -4. See, I substituted into that. 2 lots of -1 plus 2 is -4. And then the other one, which is 3, 0, then I've got f dash 3 is 2 lots of 3 minus 2, which is 4, +4. Right, so this one has a gradient of -4, and I didn't need to count anything on a grid or anything like that, and this one has a gradient of 4. Right, so I worked it out. So I could find those gradients without any diagram, but the diagram's just helping us to make sense of what this is talking about. So notice that I only put an x value in there. That came from there. The y value here is not relevant to finding the gradient of the tangent. Right, so that's C. D. Use the derivative to find the stationary point. So the stationary point is here, the vertex. The key feature of that is that the gradient of the tangent is 0. And so the stationary point occurs when f dash x equals 0, right? i.e., so f dash x is 2x minus 2, and that needs to equal 0. So I find out that x equals 1. And hey presto, this stationary point did occur when x equals 1, right? Now let me just point out, as I did in class, the most general equation of a parabola is y equals ax squared plus bx plus c, right? And so what's y dash? Well, that's 2ax plus b. That's differentiating that. And then y dash equals 0 when, so we have 2ax plus b equals 0. That's 2ax equals -b. X equals -b over 2a. Where have you seen that before? The axis of symmetry. That's how we know the axis of symmetry of a parabola is -b over 2a, right? Because we can use differentiation to know whether the turning point occurs. And question E. Use the derivative to answer the question. For what x values is f of x decreasing? So basically, we're going to solve f dash x is less than 0, right? That means f of x has a negative gradient. That's what that means, right? Well, it's easy to solve that because f dash x is 2x minus 2. We solve that for less than 0, so we get 2x is less than 2 and x is less than 1. And when x is less than 1, that's all of this, we have a decreasing graph, whereas here it's increasing, right? So differentiation allows you to find out things about a graph without actually having a graph. Very cool. Last one for this worksheet, this handout. Use your intuition to write true or false for the following. Now, there's no pressure to get this right. The point is to think about it before I just tell you. So the derivative of f of x plus or minus g of x is f dash x plus or minus g dash x. So what that's saying is if you've got the sum or difference of two functions and you want to differentiate, you just take the sum or difference of the two derivatives. Part B is the same as part A except using a product. So if you have the product of two functions, can you differentiate by doing that? And the third one is saying if you've got a constant times a function, can you differentiate by getting the same constant times a derivative? So if you'd like to pause and write true or false according to your intuition, okay, I'm about to reveal the answers. They are true, false, and true. And I'm going to explain a bit more. So, when we do something like f of x equals, let's say, x to the 4 plus 7x squared, and we use f dash x equals 4x cubed plus 14x, we are, right, so that whole logic is exactly this, and it's true, right? So this is the sum of two functions, and to get the derivative, we just take the sum of the two derivatives, right? It works perfectly well. I could go into more detail about why, but that would take a while, and I don't want to do that. Right, a bit noisy outside. I'm in a breakout room. I'm just going to pause until the noise dies down. Okay, carrying on. So part B is false, right? Now, so I'll just label that as part A, right? Part B, I'd like to consider, say, y equals, well, we had before, y equals x plus 2, 2x minus 3. X plus 2, 2x minus 3. Oh, the noise again. Anyway, so expanding, we get 2x squared plus 4x minus plus x minus 3, minus 6 rather. And now when we differentiate that, we get y equals 4x plus 1. Okay, so this is correct, right? But notice this is the product of two functions. Just like that is the product of two functions. So I'm just going to change colour. If I did this, y equals x plus 2 times 2x minus 3, if I did this wrongly, then I would be differentiating that and getting 1, and then differentiating that and getting 2, and just that. And that clearly is wrong. So it shows that we can't differentiate the product of two functions by just getting the product of their derivatives. It's more complicated than that. And turning to C, when we do something like this, so if we've got f of x equals 8x cubed, and we do f dash x is 24x squared, right? Doing the 8 times 3 to get 24, and then bringing the 3 down to 2, then we are using this, right? We're relying on that to be true. To explain, we could instead say, if f of x equals 8x cubed, then that is 8 times x cubed. So it's a constant times x cubed. And so the derivative is 8 times the derivative of this, which is 3x squared, and that is 24x squared. Okay, so we talk about just multiply that and that, but really what we're doing is we're bringing the 3 down to get there, and then we do 8 times 3. Okay? It doesn't matter which way we think about it. It's just important that when we have a constant times a function, then differentiating is easy. Okay, so in sum, differentiating a sum or difference is easy. Differentiating a constant product is is easy, but differentiating a general product is hard. More on that later.